Okay, this is a partial differential equations practice final exam at graduate school level. I'll go through this fairly quickly, and I'm going to omit some of the steps involving calculus, algebra, and arithmetic, um, just so you have answers and some explanations to the core key concepts to this exam. So let's jump right into it. So here we go. Number one, consider this PDE, partial differential equation, that we have here. We want to classify it, find change of variables that reduces the PDE to a canonical form, and solve the PDE in the new variable. So if you want to copy that or take a screenshot of it, whatnot, just pause for a second and we'll jump right into it. So let's see, for this PDE, okay, see what we can do here. Whoops, let me just rearrange this. Be right there in a second. There we go. Okay. All right, sorry about that. So, moving forward, we see the PDE. We can classify this very quickly. This is a general second order form. A uxx plus 2buxy plus cuyy. Second derivatives there. We'll let a equal x squared, b equal xy, c equal y squared. We could calculate the discriminant using b squared minus ac. And quickly we arrive at 0. So what this would indicate, we could classify this as parabolic everywhere except at the origin. 0, 0, we have a trivial degeneracy at 0, 0. Okay, so that's letter A. And I should say this: these problems take into consideration that you've completed a full course in partial differential equations, along with differential equations and applied differential equations. Okay, so part B, change of variables. We change the variables here. Okay, think of a change of variables formula. What we could do here, this original equation becomes this x, partial of x plus y, partial of y squared u. Okay, so now what comes in handy here is we're going to define r as the natural log of the square root of x squared plus y squared, or more cleanly, we're going to use radial scaling variable. Okay, so we have that xi equals natural log of r, and nu equals theta. My apologies, I don't draw the best Greek letters. So then the operator becomes second derivative here, du, second derivative over d xi. Okay, second derivative here. And for part C, we can arrive right at the solution. Second derivative here, u xi equals 0, and u equals a times nu xi plus b nu. Now if we go and back substitute this, we get u of xy equals a theta natural log square root of x squared plus y squared plus b theta. So that omitted some arithmetic, algebra, calculus, but key concepts are there. Review it. Review the concepts if you forgot how to do a problem like this. And what we could say just at the end, this is parabolic, radial log transform, solution linear in log var. Okay, so that basically takes care of that one. That's number one. And I'm going to go through these rather quickly to save time, and you could try to do them on your own, whatnot. Come back and check the answers. All right, so that takes care of number one. Now let's move forward. Let's see what we have here. Second one. Okay, so if you want to take some time for this second one and just screenshot it, copy the problem. If you want to start the problem, that's great. It's up to you. So from here, we want to let u of t satisfy that heat equation. Okay, think Fourier here, Joseph Fourier. There's an experiment, and we have homogeneous Dirichlet boundary conditions. We want to do these three parts to find what it means for U to be a weak solution, prove uniqueness of weak solutions using an energy method, and C, show that the energy functional is E of t equals limit from 0 to L integral U of x t squared dx in non-increasing time. Okay, so that is what we're doing for this second one. So this second one, okay, so I'm going to put that here. Okay, so basically what we have here, heat equation, weak formulation. We have our PDE, our partial differential equation is U sub t equals U sub xx. Now think about what we could do here. Weak solution for letter A. We could multiply the test function, okay, by phi and integrate. So we wind up with that integral U of t phi dx, right? And we have that equal to negative integral of ux phi x dx. Okay, so by definition, U in L squared, U sub x in L squared, satisfies all for phi, satisfies the above for all phi, for here and here. Okay, so this is our definition. This problem relies heavily on knowledge of the formulas related to this PDE and what transforms them. So this takes care of letter A, the weak solution. Letter B, you have uniqueness, energy method. So what we're going to do with this is we're going to let our W equal the difference between U1, U2, and then WT equals that second derivative, that X in relation to X, W sub XX. And we're going to multiply by W. And when we do that, we're going to integrate. On the left-hand side, we have d with respect to t of the integral w squared dx equals negative 2 integral of that w derivative with respect to x, first partial. These are partials. That's partial squared dx. That's going to be set less than or equal to 0. Okay. Now, if the initial data is 0, okay, then w is 0. And that would constitute uniqueness, so it's unique. All right, so that takes care of letter B. And now we have letter C, the energy functional E of t 0 to L U squared dx. We differentiate both sides. dE dt that's going to come out equal to negative 2. This is going to be the equivalent of negative 2 integral of the partial of u at x, the partial derivative of x at u, ux squared dx. So you're integrating that, multiplying it by 2, and then has to be less than or equal to 0. So we want this to be, and it's going to be non-increasing. And technically, that would be what we need for letter C. So basically, this is weak form plus energy, leads to uniqueness, and we have decay in this situation. Okay, so, and that makes sense in terms of heat. Okay, so let's move along. We have here number 3. I'll let you get number 3 down if you want to get a head start on number 3. Pause the video. Okay, so we have solve U sub t equals U sub xx, domain 0, less than x, less than pi, t is greater than 0. And then we have these conditions. U of 0t is 0, U of pi t is 0, U of x 0 is the function f of x, and that's equal to x pi minus x. And this will be very helpful for us to solve the problem. And we have 3 components, find the eigenfunctions and eigenvalues, expand f of x in terms of eigenfunctions, and write the full solution u of xt. So this requires some knowledge here with Fourier. So I'm just going to get this out of the way. You can start the problem if you want. Up to you. So, whoops-a-daisy. Just getting this ready. All right. So let's go over number 3. So we have that partial differential equation there, right? We have that partial differential equation u sub t equals u xx, condition 0 to x is in between 0 and pi. And we have u 0t equals u of pi t equals 0, u of x 0 equals x, pi minus x. That's on the previous page. So let's get the eigenvalues. So the eigenvalues here, okay, x double prime plus lambda x equals 0, x of 0 equals x of pi equals 0. Lambda sub n equals n squared, and x sub n equals sine of nx. So that has to do with prior knowledge on how these PDEs specifically relate to those eigenfunctions. Okay, so that takes care of letter A. Those are the eigenvalues, eigenfunctions. So now from here, we want to expand that initial condition, f of x equals x, pi minus x. So let's think about what we can do here. So this is where the Fourier sine series comes in very, very handy here. So f of x equals the summation of that b sub n, that's the coefficient, sine of n x. So when we manipulate all of this, think about this prerequisite here is Fourier, knowledge of Fourier series, whatnot. B sub n is going to be 2 over pi, integrate from 0 to pi x, and then we're going to substitute this pi minus x, okay, sine of nx dx. So this is substituted. When we do this work, we're going to get b sub n. So again, integrate, do the algebra, the arithmetic rather. B sub n is 4 over n cubed, quantity 1 minus negative 1 to the nth power, close parentheses. So this is only odd numbers of n, okay? Odd numbers that works for. So solution, u of xt is going to equal this sum n equals 1 to infinity, b sub n, and we change this from knowledge of Fourier, this could be e to the negative n squared t sine of n x. And think about where that comes from. Okay. Good thing is I'm not throwing everything on here. You can think about where certain things come from. If you got rusty with some things or whatnot, you could always go back and look things up, and it helps to tie things together. Okay, so Fourier sine series plus exponential decay, that's basically what this boils down to. So technically that's it for number 3. Okie dokie. So moving along, let's take a look at number 4, and you can get this down. Again, I'm going at a quick pace. Please forgive my very poorly drawn omegas. Let you satisfy this differential equation, well, not equation, it's inequality. We have u sub t minus the change in u less than or equal to 0 in omega, and then from 0 to t, cross 0 to t. So state the strong maximum principle. Prove that the maximum of u occurs on the parabolic boundary, and give an example showing why the condition cannot be reversed. So this is number 4. So you could get that down if you want, and I'll pause for a second if you or you could pause if you want to go and try the problem without any help. So just going to take these away. And we'll get right into number 4. So number 4, maximum principal for number 4. So let's see what we can do here. So for number 4, we have the PDE u sub t minus, well, technically it's not an equation form, it's in an inequality form, but it's ut minus the change in u less than or equal to 0. So technically it's not an equation now, but it's in a partial differential form. It's in an inequality. Now for letter A, if you remember, you studied the strong maximum principle. What we could say, if our u value in this situation attains an interior maximum, we know that the u value is constant. Okay, and that's according to that strong maximum principle. That's for part A. For part B, the maximum, where is it going to occur? It occurs on the boundary. We have a parabolic boundary, so we have two things we're looking at, time and space. So we're looking at initial time and spatial boundary, okay? So that takes care of the part B. Now for part C, they want to know in terms of this, we have a question. We could say, well, why is it not reversed? So if we were to do an example, if u equals negative absolute value of x squared minus t, then, okay, I just rewrote this because this was a little sloppy, sorry. U sub t minus the change in u, okay, that equals negative 1 minus negative 2n, right? Greater, and then we're going to have that's going to be, let's see, greater than 0 because we're going to get negative 1 plus 2n, right? And that's where you have your interior maximum exists. Interior maximum exists. And think about what n's, your n values could be, why this is true, why that would be greater than 0. So that's why it's not reversed. And basically that's all strong maximum principle plus boundary behavior. If you went over that during the semester, that's how you would answer A, B, and C. Okay, so we'll keep the ball rolling. We could go right into number 5. Number 5, we have u sub x plus 2uy equals u. U of x0 equals e to the x. Find the characteristic curves. Solve along characteristics. Write the explicit solution. So I'll pause for a second if you want to get that down or whatnot, and start the problem on your own. And then we'll just get this ready here. And let's see what we have here. Method of characteristics. Okay, so what we want to do is we want to find the characteristic curves, right? We want to solve along the characteristics and write the explicit function. So again, this is what we want to do, right? We want to solve this for number 5. Find the characteristic curves, solve along the characteristics, write the explicit solution, rather. Okay. So, building on that, method of characteristics, let's see what we could do here. So, our PDE, u sub x plus 2u sub y equals u, and then we have that condition u sub x 0 equals e to the x. So the characteristics, we take those we take derivatives dx ds equals 1, dy ds equals 2. And we could simply write this as x equals s, 1s plus c sub 1, and y equals 2s plus c sub 2. Okay, and by process of elimination, going through the mathematics there, algebra, whatnot, we could say y minus 2x, that's the constant. So, that's what we have there for letter A. Now, building on that, letter B, along the characteristic, if we take the derivative there, du ds, Well, if we take that derivative du ds right here, we're just going to get du ds is u. And if we want to isolate that, u equals c e to the s. I should say that's not a 5. I apologize. That's not a 5. That's an s. So that's, for part B, that's what you get for your u value. Okay. So I am skipping some steps so you could go and try them on your own to confirm. So that's the healthy part about this, is I left some steps out so you could go ahead and try to fill in the blanks, or go back and research if you need to fill in the blanks in between something, how something got to somewhere else. It helps instead of showing everything, because it sparks curiosity. So moving along the letter C, solution. Well, if we have the solution along the initial line, the x-axis here, y equals 0, for instance, u of x0, remember that's e to the x, right? Now, the solution in this case would be u of xy. If we want to write this would be e to the x, right? Times e to the negative y over 2. And if we combine using laws of exponents, this would be e to the x minus y over 2. Or e to the x minus 1/2 y, whichever you prefer. So basically these characteristics for this lead to an exponential solution. And that's all for number 5. Okay, moving along, number 6. If you want to get this down, try number 6 first. That's up to you. We consider that negative change in u equals f of x. X is in our cube, so we have 3D. And now green. That should be green. Green. I don't know how it's coming up on your video screen, but that's Green's function. So write the Green's function for the Laplacian in R3. Express the solution using convolution with the Green's function. Part C, show that the solution satisfies appropriate decay at infinity under suitable assumptions on F. So let's see what we can do here. Okay, so number 6. All right. So, whoops, let me get this out of the way. If you got this down. Okay, so number 6. So, Poisson equation in 3D space in R3. Okay, Poisson, important to remember. Okay, and let's see what we have here. Negative change in u equals f of x. So our Green's function, that's going to be, and remember, familiarize yourself with Green. If you haven't, if you forgot, go back in your textbook or online. Green's function and how the relationship between this g of x is going to be 1 over 4 pi times the absolute value of x here. Okay, that's going to be letter A. And that comes from direct knowledge of how Green's function operates. Okay. B, u of x is going to be the integral along this 3D space of f of y over, okay, it's going to look like part of the Green's function in the denominator 4 pi, but the absolute value now of x minus y, and we're going to be integrating with there to dy. Okay, so that's your solution. Okay, and if you identify a lot of things, if you know your Green's function, you could come up with this at a decent speed for letters A and B. Again, this requires pretty much knowledge of Green's function. And letter C, what we could say, this is going to decay at infinity. Okay, so this is going to decay at infinity, and we say this is compact support u of x is approximately 1 over the absolute value of x in that situation. Okay, so that's A, and that's B, and that's C. Again, I went fast, left out some things in between so you could go back and research if this piques your interest, or you may have gotten it pretty quickly. All depends on how well versed, I guess, you are with green for number 6. So Green's function convolution is basically what we're seeing here. And that's all for 6. We can move on to 7. Okay, for 7 we have u, h prime, I'm sorry, not h prime, 0, 1. Okay, think about what that h means. We want to state the Poincare inequality, and we want to prove this. Okay, we want to explain why this is crucial for partial differential equations while posing this. Now, this sometimes is these type of problems are thrown on an exam. In many cases, sometimes they're on a take-home or whatnot. So I'm just gonna go through the steps, and it's best that you look at this and try to digest it in pieces. We have the Poincare inequality here. I'm just gonna move this. Here's what we're given. Part A, here's the statement. There exists C is greater than 0 such that this has to be equal, less than or equal to this. So this expression has to be less than or equal to that. Since u of 0 equals 0, we write this as u of x is the integral from 0 to x u prime s ds. So the key to this, okay, here's our statement. Okay, this comes from the textbooks, right? And this is the expansion of what's in a lot of partial differentiation differential equation textbooks regarding this inequality, because this is just what basically we have the statement saying. This is an offshoot of what we can do to manipulate this. And now for part B, what we want to do, and I don't know if you did this in your class or not, we want to apply Cauchy-Schwarz. So we apply Cauchy-Schwarz. We're going to do here, okay, absolute value of this squared less than or equal to 0 to x. Absolute value of the derivative squared ds. So it's think of absolute value squared less than or equal to x times 0 to x. Absolute value of the derivative squared integral. We're going to integrate that with respect to ds. So we're going to integrate here on the left-hand side from 0 to 1. Think about what we're given up here. 0 to 1. Okay. 0 to 1 on the right. So there's a pattern here you can see. Pattern. Okay. 0 to 1. Okay. 0 to x. So this double integral here, because we're going to have to integrate with ds, and then after that dx. So we can do that, or in this situation, keeping this as less than or equal to left-hand side, keeping it here and here. If we keep it at the less than or equal to, we could swap the order. And what we could say is this u prime of s squared, right? U prime of s squared times that integral from s to 1 x dx ds. Okay, we could swap the order there from here. That's the key, and we could set this to an equals. Okay, and I'm just gonna move this over here so we have the full picture. So 0 to 1, absolute value squared. So this down here was equal to, this whole right-hand side becomes this. Okay? So 0 to 1. Absolute value of u prime of s squared times 1 minus s squared over 2 ds. You're just rearranging this, doing the algebra and then the calculus behind it. Less or equal to 1/2. And what we can do, just using algebra and calculus, we know a lot of this stuff cancels out. And we're going to get what we need to get. That's just going to wind up after that integration and filing it down. It comes out to exactly what we wanted to show, right? L squared, L squared. Okay, so I left some steps out on purpose because this way you could go and just go and see how all of this leads to this. So there's the big picture again. So how all of this leads to this. It's good to do this piece by piece slowly, but that arrives at that conclusion. Now, here we go for letter C. We want to know why this is crucial. Okay, so this controls a function by its derivative. It gives coercivity of energy functionals. It ensures uniqueness and stability. Okay, lacks Milgram weak solutions. I don't know if you're familiar with that or not, but it's in a lot of it's in certain textbooks. And why is it also crucial? Because if we didn't have it, norms are not equivalent, and we wouldn't be able to have that well-posedness. So well-posedness could fail. So the Poincare basically leads to the control plus well-posedness for this inequality. And this one definitely requires a thorough, in-depth pre-analysis of the Poincare inequality before doing this. Like really diving into it and studying the components of it. Okay, so that's number 7. Okay, so let's see. That is number 7, and now I guess we're moving along. A few more to go. Let me put this on here so you can get down number 8. Okay, so number 7 may have been the most, most abstract, arguably, of the 11 that we'll do. So we're on number 8. So solve u tt equals c squared u sub xx on x is in R, t is greater than 0 with u of x, comma 0 equals 5x, u of t x of 0 equals psi of x. We want to derive the D'Alembert formula, show finite speed of propagation, and interpret this physically. So I'll let you get that down if you want to pause the video. And let's see what we can do with this. And this draws on some prerequisite knowledge of the wave equation, which hopefully looks familiar. So let's build on this. So, wave equation. We have a partial differential equation here. And let's see what we can do. PDE. We want to derive that D'Alembert formula for letter A. So we were given this PDE information up here from the previous page. So let's see. Let me just get this. There we go. Everything is in here now. So we have a factor operator that we're going to need. And the factor operator is that partial, that t minus c partial x, that quantity times partial t plus c partial x times u equals 0. Okay, so that's our factor operator, and that's going to help us significantly to make this problem a lot quicker. Now, if we're going ahead and do the mathematics, and we know or if we you already knew the relationship with these already, our solution is going to be u of x t equals f of quantity x minus ct plus g of x plus ct. This should look familiar, okay? Especially in terms of this, what we're doing. This problem involves an application, just the wave equation here. Now, here's our solution, okay? We want to apply initial conditions. We substitute the initial conditions from previous page. U of xo equals this. Phi of x, u sub t of x 0 rather. This is 0, not o. I don't know why I'm saying o. That equals psi of x. So our u of xt is going to equal, when we get down to it, we want to get the final answer for letter A. U of xt is going to be 1/2 times the quantity phi times x minus ct plus phi x plus ct. And we're going to add this to this coefficient 1 over 2c times the integral bounded by x minus ct to x plus ct of psi of s ds. So this last line here gives us what we need for the answer to letter A. Okay, and that was D'Alembert formula helping us with that one. Okay, so for letter B, finite, what we were going to talk about here with speed, finite speed of propagation, the solution depends on the bounds. So the solution here is dependent on these bounds in letter A, bounds from x minus ct to x plus ct. And the disturbances travel at speed c. Okay? All right. So, letter A is a segue into letter B. And what we can say in relation to letter C, we want to interpret this physically, interpreting this physically. Physical meaning, from this, the waves are going to move from left to right. We do not have an instantaneous influence, right? So no instantaneous influence, unlike the heat equation, okay? And the domain of dependence equals light cone, okay? So we have a wave equation, finite speed plus D'Alembert, and that's it. And I left a little bit out so that you could go and try to fill in the blanks, but that's basically, that's the shell of it. That's how, those are the answers for A, B, and C pretty much. So that takes care of number 8. We'll move along to number 9, and number 9, okay, Burger's equation. So heat wave Burger's, okay. Burger's equation. So u sub t plus u sub x equals 0, u of x comma 0 equals g of x. So here's, I'll just pause this, part A, solve using characteristics. Part B, solve when shocks form. Part C, compute the shock formation time for g of x equals negative x. Okay, so this one isn't too bad. It's rather straightforward if you've done stuff with Burger's equation before. And again, I shouldn't say that like that, but it follows logical steps if you've studied Burger's equation, and it makes sense. Okay, so let's see what we have here. Burger's equation. So Burger's equation, and whoops-a-daisy, let me make sure everything is in here. Okay, there we go. All right, so Berger's equation from previous page. Here are characteristics. If we take dx dt, we get u, right? Du dt, that's 0, right? Now, u equals g of x sub 0. X equals x sub 0 plus g of x sub 0, or x naught. Some people call it x naught of t. So here's our u in terms of g of x, and here's our x in terms of x, and we have g of x here, and then we have our t. Okay, so taking this information here, we could get our implicit solution. U of xt is going to equal this, g of x naught, okay, or g sub 0. So just manipulating all of this, substituting and manipulating, we know x is x naught plus g x naught of t. So basically this is it. This is it for our letter A, for our characteristics. And this is our implicit solution that we already have from just manipulating what we know and getting those derivatives and just bringing it down here. And that's all. It's all for letter A, characteristics. Now for part B, the shock formation, let's see what we have. Shock when mapping x naught to x breaks. So again, shock is when it occurs when mapping x naught to x breaks. So if we take that derivative dx with respect to dx naught, think about what we'll get here. So we're think about deriving here. We get 1 plus g prime of x naught of t. T stays as equals 0. So basically, if we isolate the t, here, t equals negative 1 over g prime of x naught. Okay, so that's when the shock forms, and in a generality here for this, the shock forms at the minimum of negative 1 over g prime of x. This is a good thing to know. Shock forms at the minimum of negative 1 over g prime of x. All right, and this is for Berger's. And now for part C, it's not too bad. G of x is equal to negative x. G prime of x is equal to negative 1. And then we'll say, t equals 1 in that regard. Okay, so in that, at this point, Berger's, we have the shock forming at t equals 1. And that's it. And that's in relation to what we know here. Okay? What we know here and here. T equals 1 is where the shock forms. And we could say here, Berger's, we're dealing with something nonlinear, and it shocks at a finite time. Okay, so that takes care of that. All right, so moving along to number 10. We have the Differential. Okay, boundary conditions. So I'll let you get that down for number 10. For number 10, we want to show that, and I apologize for my omega not being drawn very well. Show that A is self-adjoint. Show that the eigenfunctions form an orthonormal basis. And let's see what we could do with this. Okay, so that's number 10. And we could go ahead and try this now. You could, if you got those down. For letter C, explain how this leads to solving PDEs via spectral methods. Okay, so here we go. Laplace. Number 10. Spectral theory of a Laplacian. Okay. Operator A equals negative change with the Differential boundary conditions. That's our operator. The self-adjoint. We want to check if AUV is equal to the integral of this del U dot del V. Okay? And in this situation, they are symmetric. So AU of V, AU comma V vector equals U AV vector. By symmetry, check your math. They're symmetric, thus self-adjoint in this situation. So that takes care of letter A. Okay? Letter B, orthonormal basis. Okay, we're dealing with, we have a compact inverse, leads to a discrete spectrum. Okay, spectral theorem is going to apply, so you want to go back and if you're rusty with this or haven't seen it, some professors might or might not put this on graduate's school exam based on what your professor stressed in class. Again, this is an omega. I wrote this twice. I realized this was not a well-drawn omega. This is a little bit better, but just ignore that. That L squared omega. Okay, so the spectral theorem applies. Eigenfunctions, they're orthogonal and they're complete in here. L squared of omega. Okay, so that's the orthonormal basis. Why is it useful? Well, if we expand this, U equals the summation of C sub n, phi sub n. Then the PD reduces, this is the nice thing, the PD is going to reduce to an ordinary differential equations in the form C prime sub n of t plus lambda sub n C sub n equals 0. So the nice thing about this, why it's so useful, it turns this partial differential equation into a solvable system. Okay? That's why it's so useful. So we have a Laplacian leading to spectral decomposition. And just as a side note, the eigenvalues for this are real and positive for a negative change here with this Dirichlet boundary condition. Okay, so that takes care of number 10, and we're just about done. We have one more left, number 11. Let me just get number 11 up and ready to go. You can get it down. Okay, you can get all of this down, and here's number 11. Number 11, we want to consider this. U sub t, U, a partial U, partial derivative t equals delta U plus lambda U. And in this situation, we want to determine the conditions for stability versus blah of solutions. Okay? All right. So, you could get that down. You could, again, try it if you want. And this is the last problem on the practice exam. So that's number 11. Let's go over it. So we're talking about stability. Versus blow up. We're given this PDE from the previous page. Now here's the key idea for this. The key idea is eigenfunction expansion. So what you're going to do, draw upon what you know before. We could say U is a summation of C sub n of t, phi sub n. And if we take this key idea of eigenfunction expansion, if we take the derivatives here of C sub n, that's going to equal negative lambda sub n, C sub n, plus lambda C sub n. Okay, that's if you do algebra and the derivative, and you're aware of what this could be broken up into under that circumstance. And now if we were to get this by itself, the C sub n of t, C sub n of t is going to equal C sub n of the 0, e to the lambda, e to the quantity lambda minus lambda sub n times t. Okay? Now, this is just key idea from the eigenfunction expansion and what this can look like. All right? Now think about lambdas in terms of the stability conditions. If lambda is less than lambda sub 1, the first eigenvalue. Mode should be the second. It should be, we could say, all modes as a result will decay. All modes decay. So it's stable. And if it's stable, we have this. Okay. Negative lambda sub n plus lambda is less than 0. Okay, in that situation. Given that. So that's your stability condition. And then there's the blow up. If lambda is greater than lambda sub 1, then the lowest mode grows. We get exponential growth. And think about why that would be for a function or whatnot. Or a PDE, rather. And the third condition here, borderline, if lambda equals lambda sub 1, we would get neutral stability. So stability condition, blow up, borderline, all based on eigenvalues. So the moral of the story here is stability here. Stability is governed by eigenvalues. And I know this is a lot. Partial differential equations usually takes some extra time getting used to. And reading the textbooks really, really helps in doing practice problems. But reading a lot of the stuff, that helps a whole lot. All right, well, you know that anyway if you're taking this course. I'm preaching to the choir, I guess. Well, if you're taking any exam in partial differential equations in graduate school or in any type of situation, well, I hope this helps a little bit. Hope that piqued your interest, and hope you have a great day. All right. Thank you.